Welcome everybody. This is the lecture number 15 of the deep learning course. And in this session, again, we are going to talk about the optimization into the neural network. So this time my optimization is something different, okay? What do I mean by this? So you know that what is optimization? So there is some underlying function of x. It is defined in some way. Your objective is to find out the value of x such that this function maximizes or minimizes. But let's assume that this function minimizes for the value of x is equal to 20. Okay. So how can you find out this particular value? Maybe you start by saying that since you don't know this particular value, you start initially with some value, for example 150, and see what is the gradient of this particular function. You modify it and you reach to the 110, then you reach to the maybe 70, then you reach to the 60, then you reach to the maybe 30, then you reach to the 10, then you reach, let's assume that you are not going to that particular wrong direction. So maybe by 30 you reach to 25, and then from 25 you reach to the 20. In this process, you have actually taken 1, 2, 3, 4, 5, 6, 7. Hypothetically, in this hypothetical problem, you have taken these many number of steps. Here in this class, we are going to talk about that can we reduce this number of steps? This is again an optimization step, because what happens that, as I told you, that given infinite amount of time, you can do any kind of work. So you don't have the infinite amount of time, you have finite amount of time. So right now the optimization that we are going to talk about is going to be with respect to this. So what I ultimately want to convey is that you would be still reaching to this particular value, but earlier you were reaching, for example, 1, 2, 3, 4, 5, 6, 7 steps, but maybe some other way that can directly give it here, then can I reduce this number of steps? So this is the thing that I'm going to talk about today. Make sense? So let us start our discussion. So just a quick background that all of you know, that if you have a neural network, if you have a neural network and you want to find out the right parameter, means the value of the weights which are actually here. So you can, with respect to the every input, you are going to define a kind of output, and that particular output maybe when you are going to provide something, you are expecting that I is going to be given by your circuit. For ith input, yi is going to be given by your circuit, and oi that you are actually expecting that this is the output should be at your end. So you know that you have to define a loss function, and with respect to that particular loss function, you are going to change this parameter in such a way that after some time the value gets stabilized and the distance between the oi and yi could be minimized. This is the standard procedure that I'm not talking you anything new. There are various choices for this kind of loss function. One could be the least absolute deviation, and that is just trying to see that what is the difference between the two quantities. You want to minimize this thing. Least square error, that we have seen that a square of that particular quantity. Cross entropy loss, we have also seen this into the last class. So these are some of the choices that we have with respect to the loss function. We have also seen in the last class that if it is a kind of classification problem, so this least square error is not good. And the most important thing is that this least absolute deviation is not a good idea, because what happens now, if you just try to see this particular formulation with respect to the calculus, you can say that the item that is there has only to the power 1. So what happens if you find out that what is the derivative with respect to here, so this may go away. Okay, so ultimately the overall dominance of this particular term is going to be alpha only, so nothing more than that, whatever the learning parameter that you have. So because of this, what is going to happen, let's say, since you know that weight is a vector of multiple w0, w1, etc. So if the w0 is this much, w1 is this much, w2 is this much, so what is going to happen that this particular formulation is going to reduce every item to with the value of alpha only, with something that is proportional to the alpha only. So the same value you are going to subtract from all these weights. This is not a good idea, because if something is smaller, maybe the learning rate should be adjusted based on that. So mostly we actually neglect this kind of least absolute deviation. This is not a good idea. However, in many other cases, we see that this kind of formulation of least square error is a fine, it's a good thing. But again, we have seen in the last class, because what happens that these things, there are some e to the power x means some sigmoid and other kind of non-linear activation functions are actually applied, and because of this, what happens that this function becomes what? This output function becomes what? This becomes a kind of non-convex function. So finding out the derivative becomes very difficult. So we have seen in the last class that it is a good idea to have this cross entropy loss kind of formulation of the problem. So ultimately our objective would be to reduce the error. So let's assume that we are into this formulation. We wanted to reduce the error. So how can you reduce the error? So first thing that comes to anybody's mind is this, that we are going to use the gradient descent. It is not a new technique, very old technique, and gradient, you find out the gradient and do the same thing. Very old technique. It came out into the existence around 1947 by Cauchy, and ultimately it also requires what, that if you have a database and you have the parameter w, so using this particular database you are going to reduce this w to w dash, then again scanning the same thing, w dash to w double dash. So you are changing your parameter into the step by step, and what, because it is going to be the gradient descent only, your error is going to reduce. Okay. Here comes an idea that somebody thinks that what may be possible, that what is happening now, look, the databases could be very large and there could be multiple training examples available. So what could be what is possible, that if the database is very large, so see, if the database is very large, you pick the first example, with respect to that example you find out that what is the derivative and how much you have to change. With the second example, then you find out how much you have to change. Third example, you have to find out that how much you have to change. With all the examples, you are going to see that how much you have to change. But at the time of starting, just think in this particular way, that at the time of starting, that your weights were actually not of any right shape, because they are randomly initialized. We think that the weights are random. So if you are used for the first item, you cannot do anything, you have to use this particular weight. But when you have actually find out that this much I have to change to make it correct, why don't you correct it and then you apply onto the second data? Because otherwise what is going to happen, that on the first one you are wrong, you are going to be totally wrong. We expect that, we don't expect anything that you are going to be good. And this is happening with the same second item also, they happening the third item also. However, the system has seen 3 4 items, you have done this much processing. So the better idea would be that you, with every item, you find out that what is the derivative and you update your weight. If you do like this, it is called the method is called the stochastic gradient descent. And again, very good idea. As you have seen that it's a good idea. So what happens, that earlier you were expecting that my error is going to reduce like this, but now your error would be going to reduce like this. Okay, you would be able to get more reduction into the error, but at a particular moment it may be possible that error is going up and down. All these things could be possible. This kind of thing uh, is good, but again you would not like to go to that much fluctuation. So it would be nice that if somehow you can devise a strategy that is not much fluctuating and less fluctuating. So between the completely batch based gradient descent, where you going to use the complete database to update the parameter, in between there are, you can think that I can use a mini batch kind of thing, means some items, few number of item out of this complete database. You can say that these many number of items I'm going to use. Like you can say that I have divided the data into multiple parts, and one part I'm going to use to then for this particular part I'm going to find out that how much I should change, and then I update and go into the next part. Mini batch is interesting idea, and there are very recent paper that around in 2019 etc. They actually revisited and come up to the idea that it would be nice that if you can use 30 items, around 30 items, to actually make a batch, and after every 30 item you do this gradient change, so it would be a system would be converging faster. Okay. So these are the methods that people are actually using to train the system. However, all these ideas are such that only in terms of the finding out the right parameter, it may not be useful because if you because if you have multiple number of layers, how can you find out the parameter? These things can only be applied. These things, what I wanted to say is these things are general ideas. Okay, you can apply to anywhere, but they are they may not be able to give you the right parameters if your things are into multiple layers. Once again, because the function is very complex, it is defined into neural network function based architecture. The architecture that is equivalent to a function is going to be very difficult kind of functional representation. So therefore, finding out the right parameter when the network is very deep may be very difficult. So the interesting idea came around 1986, that is called the back propagation. Very interesting paper, that learning representation by the back propagation error. This is a good paper, came out around 1986, and you also know that into the neural network history, this paper has a very significant contribution, that it provides that how to find out the uh, weights when you have a very big network. So using back propagation kind of uh, setting, also including the stochastic and mini batch gradient descent, you can train the system. Okay, so do you understand this thing what I told you, that if you have a bigger network, we all know, and into the few classes back we have seen that what is the total math, what is the overall mathematical representation of this back propagation, what is the mathematical basis for this, and we have seen that using the back propagation based system we can find out the right parameter. Okay, now till now what we have understood, that there were some problems and we were actually able to solve this problem, and now we are able to find out the right parameter. Okay, so now the next thing that I wanted to do, that how can I make this process fast? Okay, how can I make this learning process fast? So after this particular point where we are, that now we have a system that can learn the parameter. How can we make this particular system more fast? Okay, the first method that we are going to discuss is called the momentum based gradient descent. The first method that we are going to talk is called the momentum based gradient descent. The idea is this, that you know that look, you have seen this kind of curve. This actually says that initially when you are going to on the training data, if you with the number of epochs, your error is going to reduce in this particular way. So initially your error is going to reduce larger as compared to the later stages when your error is going to reduce lesser. So what does it mean? It means that initially you are going into the very fast into the error reduction direction. So if you maintain this thing, it would be a nice idea. What I wanted to tell, that let's assume that, because you know that all these things are vectors, so w is also a vector. So let's assume that weight at the time t, you find out that vt is the amount that actually you want to change. Okay, so this is with respect to the derivative only, you know that. One minute. So 1 minute. So what I wanted to tell you, that my basic idea is this, that here the gradient is high and here the gradient is lower. So if I somehow maintain, because these things are also making the thing correct, can I use some of the force from here and also maintain that particular force at this particular place? So what I expect, that maybe my curve would go into this particular direction, my curve may go into this particular direction, and this is what if I can do like this, if I can do like this. So what I'm telling, that I am going to push the things into this particular way. If I can do like this, what would happen? that at a particular point of time, if I wanted to see that if I'm going to run to this many number of epochs, I can see that I would be able to achieve the lesser error as compared to the previous one. This is the idea. How can I utilize this idea? So at the previous moment, what was the change I have done? Let's assume that, because every time because you started by a weight and then you change this weight to w dash, then you change to weight to w double dash, and so on. You are going to change this particular weight. How you are going to change these weights? You are adding something. How much what you are adding or subtracting is vt. Let's assume that vt is a value that you are going to change. So I'm not writing it W right now, because you may think that right now how much I have to at a particular moment t, how much you have to change. So you find out the function that is parameterized on W, you find out what is the derivative, and we can call it that the derivative with respect to the W. So with respect to the derivative, so by seeing the value of derivative with respect to this particular W, this is the amount generally we want to use, because what is our general setting is that W is equal to W minus gradient multiplied by some alpha. This is how we actually modify. So if this much I wanted to modify, what I wanted to tell that this much somebody is suggesting, the system is suggesting me to modify at this particular moment, but few minutes back how much actually updated. So let's assume that into the previous step I have updated the thing with the value vt, means the w was actually w minus vt. This is how it has been changed. Let's assume that w t minus 1 whatever value was there, and if I want to find out what is this value, this is how we have updated. And here in this particular formula, what is this particular quantity? You know that it is some alpha time, it is with respect to the derivative only, that what was the derivative at that particular thing, there is some alpha multiplied by this and some more terms. I don't want to go into much detail because it is going to be a recursive thing only, because what I am going to do right now, the same thing has been done earlier also, so there is a recursion. So I just wanted to focus on this particular quantity, that how much I have updated into the previous time. So if it is Vt, I can say that I can multiply with some gamma to Vt, and whatever with respect to the gradient, whatever I am going to get over here, I multiply this with the alpha, and this particular quantity that says that summation of both of these quantity is going to tell me that how much I am going to change at this particular moment. Once again, how much you have changed into the previous step, what is the gradient that what it is the gradient suggesting, and then you are going to properly weight them, that how much you want to give weight to the previous thing, how much you want to give the weight to the current thing. Using this you find out that how much you have to update, and then using this kind of formulation you say that you are going to update your weight, and you are telling that wt is equal to wt minus 1 minus this particular quantity vt. Any problem in this kind of formulation? Once again, if you do this kind of formulation, what would happen, that earlier your things were like your error was going to reduce like this, but now your error is going to reduce like this. So this is a better method, and it is going to do a kind of optimization in your time. Now you can train your bigger system in a less time. Any problem on that? Please ask if you have any questions.
So there's a chance that if alpha's value is like kind of on the bigger side, that the error will start increasing again, right? Because like maybe you optimized it and then you're at the optimized state, but you're forcing another change based on previous changes.
Uh, Very good observation, Mohit. So we would discuss this thing later, and this is the first method. So definitely you are telling the right thing. But right now, any other question? This would come. Whatever you are telling
So
would
what
come
is
later.
Vt minus 1 if
Okay.
del
So
W is
how
defined
much
as the
how much
gradient?
change I have done few minutes back? So first change was V0, then V1, then V2, then V3. Then at this time I want to find out how much I have to change. This is what the VT. Every time whatever change you have done, you are going to maintain this in some memory. So use the previous value, that is called the Vt minus 1, and you multiply with the gamma, and then on the function you find out that how much you have to change, that is going to be your derivative, and you apply, you multiply with this, with the alpha, and this quantity is going to be your Vt minus Vt.
So why is there a T minus 1 subscript in both of them? Shouldn't one be T if both are
Uh,
from the previous step?
so Vt minus is fine.
Yes.
At the time t, if I wanted to find out Vt minus 1 is fine.
Hmm.
Vt, if I want to find out, this particular part is fine. Okay. So you want to tell that why don't we put it here Wt? Okay. So no
Hmm.
problem. It is just a matter of just representation. Sometime if you understand this thing, that uh, what is
Current
the
gradient.
gradient at that particular point, I wanted to find out that.
Yes, sir. Hmm.
It's okay.
Okay.
However, you can see that since you are going to change something, try to understand this, that it would become a new weight, and on the new weight there would be new loss. On that loss, if you find out what I'm telling now, that weight right now, weight, let's assume that it is the weight at the time t, if I want to find out, and change at the time of t, I'm going to find out at this particular moment. So previous weight need to be added this particular quantity. So on this, what is the error? It would be the future thing that is going to be error for me now. Okay,
Yes,
so
sir.
as I'm telling that it is not going to be a difficult things to see that whether we should put t and t minus 1. It is just a matter of just a uh, uh, nomenclature only. So you can decide that I'm going to put whatever value right now. So the basic idea is only this, that right now whatever you are going to be, so ultimately w t plus 1, here you can say that this is not t, this is t plus 1, you can say like that. Okay, and then you can say that here it is wt, and then at the time t plus 1 I'm modifying, or t minus 1 modifying. This is the basic idea.
Yes, sir. Understood.
Am I audible? I think there was
Yes,
just some
sir.
problem in my
Yes,
connection.
sir, in
Am I
between your voice left, but now it is.
is it fine?
Yes, sir, fine.
Sorry, there was some interruption in my side. So what I wanted to tell here, that it is just a matter of convention, that to whom you are writing t and t minus 1, you try to understand that what is because whenever you are going to add something, you are going to get the things further new. So you may sometime you may like to write that if you want to find out that what is the weight at the time t plus 1, you are going to use what is the weight at the time t, and then you v t, you can write like this. It is just a matter of convention. Okay, try to understand that what I have done earlier, uh, what I have done at this time, what is going to be there, this is going to become vt minus 1 plus gamma time plus alpha time derivative of w. Okay, any questions?
No, sir.
Okay, Mohit was telling a very interesting thing, that he was telling that if it is you know that it's a optimization problem. So what may be possible, that since you are here at this particular point, if you want to find out how much you have to change, just you find out that this much you have to change, but previous value is going to give you something else, some value he is also going to give me. So based on these two things, so instead of using this much to change, this much change is coming from previous one, so ultimately you end up changing this much. So it may be possible that you reach at this particular point. So what would happen, that at this particular point, if you again find out that what is my change, then it would keep you, if you bring you this side, and then again from here to here, here to here, so oscillation can happen. Okay, so Mohit is telling perfectly correct thing, and this is the next algorithm that Nesto accelerated gradient, that actually try to see that this kind of problem may happen, that I can do a overshoot, that a overshoot can happen, that a overshoot momentum could overshoot the local minima. If there is any local minima, then it can overshoot. Okay, there is a minima point that we can overshoot. So what should be the good method? That the good method should, whenever it reaches to some place, it should only be, it should take smaller baby steps when it is going to reach to that particular minima. So how can I incorporate this part? So Nestor actually proposed this idea that when you are going to find out the derivative, so where I'm going to find out the derivative, let's assume that I am at this particular point. So I am actually finding out the derivative at this particular point. Okay. It is telling that you do one more thing, that you add whatever value you want to add to the thing and see what is the next function. So next function after adding, you, this is the next function. So on this particular value, you find out that what is the derivative. Use this particular derivative to update at this particular place. The idea is that find out what is the future value, find out what is the weight, future value of the weight by using the t minus 1, and this is defined into this particular way, that what is the weight at the time t minus 1, then gamma time whatever you have done update at that particular, at the previous moment. Using this, you find out that what is the weight over there. You find out the weight at that point, you find out that what is the derivative at that particular place, because with this you can parameterize the neural network and find out that what is the derivative with respect to your uh, weight, and the whatever you have done the update into the previous time, use that particular value, and at the future time whatever the update is there, you combine both of these two things, and then you properly weight them, and then you tell that this is much I am going to change. This is an interesting idea that that is called the accelerated gradient, and it is superior to the momentum. It is superior to the momentum based system that we have seen just now. Can you see the idea? The idea is this. Idea is only this, that whenever you have this particular value, earlier you were finding out what is the derivative at this particular point. But now I am telling that you find out the new parameter and find out the derivative at this particular new point, and use this thing to update this particular value. Using this kind of idea, this is a better optimization strategy. This is called the Nastro accelerated gradient descent. Okay, so if you understand this thing, so everything is fine till now. Only issue is this, that what happens that because weights are, there are multiple weights, na? Because on my system, on my neural network, everywhere there are weights, so multiple weights are there. So if we apply a gradient based method where I can say that I am going to put alpha as a multiplying factor to this particular gradient, that may not be the good idea, because some values are actually higher, some value are actually lower. So how can I adapt this particular learning rate also, so that when the value is higher, then the gradient is higher, the value is lower, maybe the gradient is lower. How can we do this particular part? Next idea is called the EDA grid. Okay, next idea is called the EDA grid. Interesting idea. That actually maintains one more variable, and please focus this thing. There is one more variable that is called the VT, and VT is, what is this VT? What is VT minus 1 plus gradient at that particular point square, gradient of that particular point square of that particular quantity. So initially you may think that VT is equal to some initial value, or you can say that it is 0, and V1 is equal to 0, then it becomes V2, then it becomes V3, and so on. And right now at the time t, when you are going to update the thing, you are updating in what way? So what is the general way of updation? Updation is this, that you find out that what is the gradient, and with the gradient you multiply a constant, and previous value you are going to subtract with that. This is what the formula is. Now I am telling that this, earlier it was a alpha only, but I am telling that instead of alpha use this formulation, and which is some variable eta divided by under root of Vt plus epsilon. Epsilon is just a small number, as I'm telling that epsilon is just a small number, so that if Vt is equal to 0, then it doesn't become 0. Eta is again a parameter, a small parameter that is very similar to the alpha. But now you can see that this particular quantity, as you are increasing with the number of epochs, Vt is going to increase, because every time it is going to add something. Okay, here every time I'm going to add something. With this, the value of Vt is going to increase. So this particular quantity is going to reduce. So every time my learning rate is going to reduce. This is mostly happens. You know that if we, on whatever surface you are, if you keep learning, what is going to happen, that ultimately when you are going to reach to the local minima, at that time your speed should be lower, because here you can see the gradient is lesser as compared to the previous places. This is the idea. So this idea is called the EDA Grid. Okay, adaptive.
So what is the new here? Just a parameter.
Yeah. So it is just like an alpha. You can say that
Okay. Yes.
it is again a number, a small number.
Yes.
And this epsilon is just to tell that it should not be 0. This is ultimately going to be a positive number. So for the initial things only, it is going to be something. So this is how you actually come up with this kind of idea. Square you are adding, so definitely every time it is going to be increase, and that's why this value is going to decrease, and this way you are going to train your system. Okay, this method is called the EDA Grid. So this is a good idea. That, but however, can you can you tell me any special advantage of this particular method? One very important point is this, that it take different step size into the different dimensions. Different dimensions. Different step size into the different dimensions. Different dimension means what? Different weight. So weight, you know that weight is a weight vector with W1, W2, dot dot dot. So based on the W1 and W2, how they are going to change using this quantity, this particular thing is going to change. So your learning, your step size is going to be dependent upon what? That what is the uh, that is, I should not say this thing. I should say only this, that based on the properties of this particular um, parameter, this learning rate is actually going to adjust itself. So now every parameter has its own learning rate. Very interesting idea. So is there any issue with that? Is there any issue? Or do you see that anything that could be more significant into this particular direction? So one observation is this, that you know that multiple times we are telling that this is how we expect that my training rate is going to reduce. So earlier, at the initial time, it is going to be higher rate. After that, it is going to be at the lower rate. So when I'm going to come at this particular point, so I may be more interested in what is happening in nearby area, not here what has happened long back. Understand? So I would like to be more influenced by whatever is the thing that is into the nearby area, not here, that is very far away. So how can I say that? Because this particular formula is a summation formula, so everything has been added. So everything is going to be contributing, going to contribute into this particular discovery. Can I tell that remove these parts or make them less significant? How can I do these kind of steps?
Sir, but here VT, although it is summation of everything, it is just affecting the rate of learning, right? It is not affecting the actual change value exactly,
Correct.
like
Yeah.
on what it is based, right?
Correct. Correct. But actually, you know, na, at whatever point you are, Gradient is not in your hand. Gradient is going to be a number,
Hmm.
because gradient is gradient. So it would be there. You cannot tell anything about that. Is somehow if you can increase, if you can find out the right parameter at this particular thing, so very quickly you would be able to reach to the optima.
Yes, sir.
So your objective would be to adjust this particular parameter in an effective way so that you can somehow reach to this particular place early. Now my question is that why this particular part is having all these things? Cannot it only see that what is happening at this particular place, and based on that it can adjust itself, so that then maybe it can take the better decision that what should be the right value, and I can reach to this particular to the optimal value quickly. So the idea is only this, that whatever things has come earlier, can I somehow reduce their importance? Okay, this happens. This can only be done if you say that I can use some kind of parameter that I can multiply with the previous value. Let me give you a kind of formulation. So I can, let me say in this particular way, so that if I say that, for example, there is some value v1, some value v2, and some value v3, v4. v2 is equal to v1 plus delta sum square. v3 is equal to v2 plus delta square at that particular time. v4 is equal to v3 plus delta square. If this is what the formulation is, what if I put an extra term, say beta here? I say beta over here. I say beta multiplied by this. And this beta may be 0.9 right now. Just try to understand. So what would happen? This particular equation becomes what? Beta time v3 means what? Beta time v2 plus some delta square plus delta square. So try to understand, all these deltas are not same. Is it right? The same formula. And here this thing becomes what? Beta of beta time I can put v1 plus delta square. Outside there is delta square plus delta square, something like that. So you can see that if you completely open this, you find out that ultimately the formula becomes beta to the power 1 to beta to the power 3 v1 plus plus whatever delta earlier has, it has beta. You can see that it is beta cube beta square plus beta time delta, previous delta 1 delta 2. I think should I write the formula into correct way so that it make you more sense? Okay, so what I just wanted to tell you is this, that is this, that v1 is equal to, say I say x, then it is, if I say that beta time v1 plus delta, let me write delta 1 delta 2, and it is the square of that quantity, beta time v2 plus delta 3 plus beta time v3 plus delta 4. So here if you open the last one, you can see it is going to be something, because this beta v4 is equal to what? Can you help me find out that what is the value? It is delta 1 multiplied by how many times? 1 2 3, beta cube delta 1 plus beta square delta 2 plus beta time delta plus delta 4. Am I right?
Yes, sir.
Yes. So you can see that whatever has come earlier, this particular thing has come at the first time, this has come at second time, this has come at third time, fourth time value. They are multiplied by beta. So beta, this is 0.9, but this is 0.8 and this becomes 0.7. Okay, it is a damped model where the previous thing, when they are multiplied by some kind of quantity, you can say that they are going to be given the lesser weight as compared to the current weight, maybe. So one different formulation could also be this, that you can say that V1 is equal to Vt is equal to you can say that beta time Vt minus 1 plus 1 minus beta time whatever delta you are going to get at the right time. This is this also a similar kind of formulation. I am using a parameter beta, 1 minus beta over here. So I can say that how much I have to give this importance to the current thing and how much I have to give the importance to the previous thing. And since beta t minus 1 is here, so it is going to have all the history. But if you go deep down, you can see that the effect of the previous thing is to be reduced. So this is going to be something like you can think that it is the effect of the things are going to be reduced. If you see that back very old things, their effect are going to be very less. Can you tell me that you understand this formula?
Yes, sir.
If I change this formula into this particular way, the method is called the MS prop. The method is called MS prop. Here, once again, don't go to this particular much things over here. They are the same thing. The paper actually mentions instead of VT small term, it says that expectation of GT square T at the time T at that what is at the time T minus 1. Just see this particular thing. So there is a beta term and 1 minus beta term multiplied by what is the gradient at this particular moment. In the weight update formula, same kind of weight update formula it is again, once again, that whatever the previous value, and then you are going to multiply with weight, and what is inside? Inside is this eta divided by under root of this particular quantity. This is called the MS prop. Any problem on that?
So the equation you wrote on the last page is the RMS prop equation.
This
The one
equation.
written below. This
Yes.
RMS prop.
Yes.
But in this RMS, why are we putting 1 minus beta? Like, why couldn't we
So
just
look,
let it be 1?
look what happens now. Here also I have to put some kind of weight to tell that how much I am going to weight to this particular part. So beta and 1 minus beta, whenever I put this thing, that does say that how much I am interested to see that whatever the previous thing, how much I give importance to the current thing.
Hmm.
Okay.
Okay.
So into the MS prop formula, this is how I compute the expectation of G square T. So forget about this. It is just a VT kind of thing. Just see that. Just consider it as some constant at the time T, some constant at the time T minus 1 and so on. You put the square root of this quantity over here. Epsilon is not needed because initially when you start, you would be having some value. We expect that it will start from that. The same formula. Any problem in this particular formula? Yes or no? So what I told you that at the time T, if you want to find out something, I was telling that the give previous things very less weight. Okay. So there could be another method. You can say that, okay, why should I give them weight at all? Why don't I only consider this particular part? Okay. For the last T times, whatever the value that was came to me, I use this formula to update this particular quantity. Yes or no? One way this could also be there. Na? Instead of, as I'm telling, the damp window means I'm going to consider all these things and adding this thing. Instead, it may also be possible that you say that, okay, I'm going to consider this particular part only. So this is another paper that is called the EDA Delta. And interestingly, these two papers came into the same year, 2012. So this paper is also of the 2012. So they were independent work. They were doing the things on the same line. Here the paper says that from the time 1 to 2, I'm going to see that what is the change over there. So the similar kind of formulation this paper also puts and come up with the same kind of equation. And this particular formulation is called what? EDA delta. Okay, with the small, very minimal changes. This paper is called this EDA delta.
So what
So
is the change exactly? Because the formula is remaining same.
formula, the difference is this, that it is going to find out the summation for the last T terms only. It is neglecting all
Manually, it
these
will
terms.
find the summation.
Yeah, it is not multiplying. It is telling that these T terms I'm going to consider
And
for the
while considering those T terms, even there they are applying dampening.
same formula. Yeah.
Okay. Yes, I got it.
Okay.
Mm.
Then comes the very interesting idea that is called the ADAM. Today, many of the places you can see that there is a optimizer called ADAM optimizer. Came in 2014. The paper came into 2015. Archive paper came in 2014. This actually combined both the MS prop and the momentum. And the idea is very simple. It tells that I am going to maintain two parameters, each for one for the how much I have to change and another for how much I have to use for the for the learning parameter. So it is going to maintain two values. Mi is equal to beta. There are two parameters. I'm telling that beta 1 and beta 2. Okay. This parameter is with respect to that how much I have to modify, how much I have to modify the weight, and this is going to tell with respect to the what is my current gradient. So on the gradient I am going to multiply 1 minus beta 1 and beta 1 time whatever the gradient was earlier. So these two values I am going to use. By this I am going to utilize momentum. I am going to find out this mi value. MS prop thing that what should be the multiplying factor, what should be the multiplying factor or alpha. Two things na, there is a weight part is being maintained by computed by this formula. What should be the multiplying factor, that is computed by using this formula. It is again the same formula here. A different kind of weight I am going to use, and this weight is actually beta 2 1 minus beta 2, and here gradient is square, summation of gradient square is there. Two values I am going to compute, mi and vi. Then this paper also says that there is some corrected estimation that it obtains by just putting this particular mi is divided by 1 minus beta 1 to the power t, and vi is equal to vi estimate is equal to vi divided by 1 minus beta 2 to the power t. So using this formula is modified, find out that what is the estimate. Using this formula, it find out that what is the estimate, and then mi, using the mi and using the vi, it find out that what should be the multiplying factor, eta divided by this formula you see na, eta divided by under root of vi plus epsilon multiplied by mi. The similar kind of formulation, and using this kind of formulation, it says that I am going to update my parameters. This is a kind of graph that is shown into the same paper, the paper that appeared in ICLR 2015, ADAM, a method for stochastic optimization. You can see that the comparison with all the methods are actually provided over there. You can see the ADAM optimizer has the lesser, it is going to be like this as compared to the other ones. You can see that they are going to take the, they are going to have the lesser reduction into the error as compared to the ADAM. So ADAM is faster. This experiment is done on the AMNIS database, that is the database of digits. Okay.